Welcome, I am Piero Rivera Benois, and I work in the Signal Processing Group at the University of Oldenburg in Germany. In this presentation, I will present a novel optimization procedure to design a fixed feedback ANC controller for in-ear headphones with multiple loudspeakers, which aims at minimizing the sound pressure at the eardrum by using a virtual sensing technique called virtual microphone arrangement technique. The outline of this presentation is the following. First, I'm going to give you an introduction into the topic of active noise cancelling headphones, followed by a description of how we use the virtual microphone arrangement technique to minimize the sound pressure at the eardrum instead of at the inner microphone. Third, I'm going to present you the proposed optimization procedure with a convex objective function that we use to derive a fixed multi-loudspeaker ANC controller. Fourth, I'm going to present the simulation results with which we showed that the proposed multi-loudspeaker ANC controller outperforms its single loudspeaker ANC controller equivalent. Finally, I'm going to finish this presentation with a summary of the most important findings of our work. ANC headphones aim at minimizing the environmental noise at listeners' ears. These devices combine the passive attenuation achieved by the construction materials of the headphone and the active attenuation achieved by means of ANC. While passive attenuation is mainly effective in the mid and high frequencies, ANC is mainly effective in the low frequencies. At your left-hand side, you can see the in-ear headphone that we consider, also known as the earpiece. At your right-hand side, you can see a schematic of it, where it's two loudspeakers, here and there, and the inner microphone, at this position, can be seen. In the presence of an external noise source, noise leaks through the device into the ear canal. It first arrives at the inner microphone as R of N, and finally reaches the eardrum as D of N. Simultaneously, the ANC controller generates the control signals U sub 1 and U sub 2 to drive both loudspeakers, aiming at generating a sound wave that destructively overlaps with the sound wave of the incident noise. ANC approaches filtering the inner microphone signal to generate the control signals are called feedback approaches. These feedback ANC approaches can exploit the proximity of the inner microphone to the eardrum. However, since the sound pressure at the inner microphone and the eardrum cannot be assumed to be the same, virtual sensing algorithms have been proposed that aim at moving the sound of quiet from the inner microphone to the eardrum. The virtual sensing algorithm that we use is known as the virtual microphone arrangement technique. It works using a two-stage approach. In the first stage, called the calibration stage, a probe tube microphone is placed at the eardrum that is depicted here in pink. Afterwards, the in-ear headphone is inserted into the ear. With the DSP depicted here in blue, the acoustic paths between each loudspeaker and the eardrum, called the secondary path S, as well as the acoustic paths between each loudspeaker and the inner microphone, called feedback path, or B sub R here, are measured. After all measurements have been performed, the probe tube microphone is removed. During the second stage, called the control stage, it is assumed that the measured acoustic paths remain more or less unchanged after removing the probe tube microphone. The measured acoustic paths S hat and B hat are then incorporated in the ANC algorithm as internal models to make online approximations of the sound pressure at the eardrum. This is done by following a three-step approach. First, the measured acoustic path B hat is used to cancel the control signal at the position of the inner microphone, and through this estimate the noise sound field at the inner microphone R of N. Second, the sound field at the eardrum D of N is approximated using R hat by assuming that for the noise source, the sound pressure at the inner microphone and at the eardrum are equal. Third, using the estimated signal D hat and the measured acoustic path S hat, an approximation of the sound pressure at the eardrum E of n, is computed. This estimated sound pressure at the eardrum E hat is used as input for the single input multiple output controller W. In the following section, I'll present you a novel optimization procedure to derive a fixed multi-loudspeaker ANC controller that uses the virtual microphone arrangement technique and an approximation to overcome the non-convexity of the objective function when it is assumed that the ANC controller is a single input multiple output FIR filter. For the filter design, we aim at optimizing the controller W to minimize the power spectral density of the sound pressure at the eardrum. The PST of the sound pressure at the eardrum can be written as follows. The left-hand term determines the minimum achievable PST at the eardrum, which is 0 when the magnitude square coherence between D and R is equal to 1. The right-hand side defines the scope of the optimization of the controller W, where it should be noted that both the numerator and the denominator depend on W. Aiming at simplifying the scope of optimization of the controller W, we make the following assumptions. As already done for the estimation of the sound pressure at the eardrum, we assume that for the external noise source, the sound pressure measured at the inner microphone and at the eardrum are equal. Second, we assume that after removing the sound probe microphone, the secondary path S remains unchanged. Third, we assume perfect knowledge of the feedback path B sub R by measurement. As a result, the equation simplifies to the point where only the denominator depends on W. Nevertheless, it should be realized that an optimization of W by direct minimization of this equation is not straightforward due to the non-convexity of the optimization problem. Instead of minimizing this non-convex objective function, we propose an alternative formulation where we maximize the denominator of this equation in the DFT domain, leading to a convex objective function if we assume the controller W to be a single input multiple output FIR filter. Here, G1 denotes a frequency weighting function. This convex objective function is maximized subject to several inequality constraints, namely a stability constraint based on a single-sided hyperbola, a maximum amplification constraint set by G2 that aims at controlling the waterbed effect, and a maximum controller gain, which is given by the function G3. These inequality constraints need to be satisfied for each frequency, and in the case of the last constraint, also for each loudspeaker channel. In our optimizations, we set the three frequency-dependent functions G1, G2, and G3 as shown in the plot on your right-hand side. G1, in the cost function, weights the lower frequencies more than the mid and high frequencies. G2 limits the maximum amplification to 4 dBs, and G3 limits the gain of the controller to a maximum of 26 dBs in this region. In the following section, I'm going to present you the simulation results with which we compared the proposed multi-loudspeaker ANC controller with its two single loudspeaker ANC controller equivalents. In our simulations, we used impulse responses measured with a dummy head and a hearpiece, which is equipped with 2 loudspeakers and an inner microphone. With these measured impulse responses, we simulate the acoustic transfer functions from the loudspeakers to the eardrum and to the inner microphone. The parameters are set to the following values, and 3 controllers are optimized for the same total number of 128 FIR filter coefficients. The first 2 controllers are single loudspeaker ANC controllers that use either the loudspeaker 1 or the loudspeaker 2. And the third one is the proposed multiple loudspeaker ANC controller that uses both loudspeakers. For all simulations, the internal models in the DSP are set equal to the acoustic transfer functions. As noise source, a diffuse sound field is generated by 47 uncorrelated noise sources, and the PSD of the sound pressure at the left eardrum is used for evaluation purposes. The results are shown in 3 magnitude versus frequency plots. The plots on the left and the middle correspond to a single loudspeaker ANC controller, either using loudspeaker 1 or loudspeaker 2, whereas the plot on the right corresponds to the proposed multi-loudspeaker ANC controller using both loudspeakers. In each plot, the PSD of the sound pressure at the eardrum is depicted in red for ANC off, which is the same for all 3 plots, and in yellow for ANC on. By subtracting both curves, the blue curve is created, which shows the active attenuation achieved by the ANC controllers. I have marked in red the area below the curve which corresponds to an amplification of the PSD, and in green the area that corresponds to an attenuation of the PSD. If we concentrate only on the red areas, we see that for all ANC controllers an amplification is produced, whereas this amplification remains below the maximum amplification of 4 dB specified by G2 up to 4 kHz. It exceeds this value for higher frequencies. This may be due to the fact that the assumption that D and R are equal does not hold in this frequency region, because the wavelengths are comparable to the distance between the inner microphone and the eardrum. However, it should be noted that this happens in a frequency region where the passive attenuation of the in-ear headphone is very high. If we concentrate in the green areas, we will see that the multiple loudspeaker ANC controller clearly outperforms both single loudspeaker ANC controllers by extending the attenuation bandwidth to frequencies below 20 Hz and incrementing the attenuation magnitude by up to 10 dB for frequencies below 300 Hz. Now we have reached the conclusions. During this presentation, I have shown you a novel optimization procedure to derive a fixed multi-loudspeaker ANC controller that aims at minimizing the sound pressure at the eardrum. The convex objective function with multiple constraints is both applicable to single as well as multiple loudspeaker ANC controllers, whereas during the optimization only loudspeaker to eardrum transfer function S is required, the loudspeaker to microphone transfer function B sub R is also required during the control stage as internal model for the real-time estimation of the sound pressure at the eardrum. Using acoustic transfer functions measured with an in-ear headphone prototype with 2 loudspeakers, the proposed multi-loudspeaker ANC controller was compared to 2 single loudspeaker ANC controllers using the same total amount of filter coefficients. Simulation results with a diffuse noise field showed that the multi-loudspeaker ANC controller effectively improves the attenuation by up to about 10 dB for frequencies below 300 Hz when compared to both single loudspeaker ANC controllers. So, we have reached the end of this presentation. Please do not hesitate to contact me if you have any questions. Enjoy the rest of the conference and see you next time.